laws of motion, or a more sophisticated version of that, Hamilton's equation, with which you can figure out how position and momentum coordinates would change with time. So if you have the initial, if you know the initial state, then with the help of this time evolution equation, you can calculate what will be the state after some time. So MHD also has this kind of structure. So let us first figure out how we prescribe a state in MHD, and then we shall look at the time evolution of the equation. So first let us consider a state of a fluid, and then we shall consider the expansion to MHD. So a state of a fluid, how do you specify it? Suppose you have a gas in a cylinder, and in your thermodynamics course you must have learned how to describe the state of a gas in a cylinder. So how many thermodynamic variables do you need?
Pressure, volume, temperature.
Well, are they all independent? How many independent? Yeah, that's right. You need two independent variables to specify the state, and when you are in a continuous situation, maybe the appropriate variables may be some rho and p. Of course, instead of them you could have used other variables also, temperature or entropy, but only two of them are independent. And if you are considering a situation of a fluid in which things are changing from point to point, then these things also will be a function of position variable, unlike what happens inside a cylinder where these things are constant. And also in a fluid you can have some flow velocity, so that will be an additional parameter. So Vx, and remember that V is a vector, so you have these two scalars and three components of V are the three scalars. So you have 5 scalars. If you prescribe the field of this 5 scalar, then at a particular time you know the state of the fluid. So now let us consider the extension to MHD. So what other additional variables we need? So you may think that we may need energy, electric field and magnetic field, but it turns out that we don't have to consider the electric field. So it's exactly for the reason why when you're solving electrostatics problems, you can assume the electric field to be 0 inside a conductor. So that is because if there are free charges inside a conductor, so if there is an electric field inside the conductor, the free charges move around and very quickly the electric field gets screened off. So a plasma is also a very is also a very good conductor of electricity. So that's why it is in the rest frame of the plasma we do not expect much electric field, but the large scale magnetic field is there, and because we don't have magnetic monopoles, and in fact in the morning I talked several works of Parker. So one famous work of his was that he used this existence of magnetic field in the galaxy to put some constraint that there could not be too many magnetic monopoles in the galaxy, otherwise galaxy magnetic field also would be screened away. So that is called Parker limit. Anyway, so since we know that magnetic monopoles are not there, so there can be large scale magnetic fields in the plasma, but not large scale electric fields. So apart from these variables, the additional variable is this magnetic field. So a state of the plasma is described by, so these are 3 scalars and this is also 3 scalar. So 8 scalars, so rho, p, components of velocity field and components of magnetic field. These prescribe a state of the plasma. So now our job is to find out the time derivative equation of all these quantities. So let us discuss that quickly. Maybe the things which I am going to discuss, some of you may know. So for those about 5 or 10 minutes, there may be a repetition. But since it seems that it appears that some of you don't know these things, So it's better to to discuss this thing. So we are now considering time derivatives, and in fluid mechanics or MHD we can discuss two kinds of time derivatives which are called Eulerian versus Lagrangian. So what are they? So Eulerian time derivative is something, suppose at a particular point in the plasma you find out how some quantity like pressure or temperature, how quantity is changing with time, and that is called Eulerian time derivative. And on the other hand, you consider some small element of the plasma and which may be moving, and you think of moving with this small element of plasma, and as the small element of plasma is moving, you try to find out how some quantity like pressure or temperature would vary within this moving fluid element, and that is called Lagrangian time derivative, and they are related. Let's quickly work that out. So this Lagrangian, suppose here this blob was in position x at time t, and now it has come to x plus delta x at time t plus delta t. So let us consider some quantity q, which may be temperature or pressure or something like that. So how do you, this is the Lagrangian time derivative of q, which is denoted in this fashion. So how do you define that? So this delta t going to 0, and we have a difference of q for when the blob has come here, and what is q here. So that will be like q x plus delta x t plus delta t minus q x t and then delta t. And you know how to proceed in such situation. You make a Taylor expansion and keep only the first order term, and that will give you, if you make the Taylor expansion of this, that will give you qxt plus delta x plus grad q, and then delta this delta t and minus this term. You can see that this will cancel with that, and there is delta t at the bottom. So this delta t will cancel with that, and delta x by delta t is nothing but the fluid velocity v. So this is going to be equal to, so this is the Eulerian time derivative, which is usually denoted in this fashion, and then this is going to be this v delta x by delta t gives you v delta q. So we can write down an operator of this form connecting this Lagrangian and Eulerian time derivative. So if you can find out one of the time derivatives, Eulerian or Lagrangian or something, you can easily get the other kind of time derivative. So when we are discussing this problem of finding these time derivatives of these quantities, we just have to figure out one kind of time derivative, then we can find out the other one. Okay, so let us first consider this time derivative of density that is given by equation of continuity, which some of you may know, but let me just quickly discuss that for the sake of completeness. Suppose you have some fluid inside this volume, and this mass of this fluid inside this volume would be this rho dV, where dV is we call considering the volume integration of this volume. And this mass inside this volume that can change only if there is some kind of mass flux inside or out of this volume. So suppose you consider this region in the surface, and you easily can figure out that the outward mass flux would be given by this. So this rate of change of this mass in this volume, that will be given by this mass flux all over the surface, and that is this rho v dot ds. And if there is outward mass flux, then that will reduce this mass inside the volume. So you have to put a minus sign. And this is a surface integral which you can easily convert to a volume integral by this Gauss's law. So Gauss's theorem. So the volume integral will be divergence of rho v and dv, and you can bring it on this side, and if you interchange this integration and time derivative, which is usually not a problem, then you would get this del rho del t plus divergence rho v dv is equal to 0 by bringing it on this side. And since this has to hold for any arbitrary volume, so this part must be 0, and this is the celebrated equation of continuity. And so let me write it here, all the basic equations I am writing here, and then yeah. So we have got time derivative equation for one of them, and one can also derive a time derivative equation for pressure P, but somehow that is not going to be very important for our discussion. So let us not bother about that time derivative equation. So let us come to the time derivative equation of V, and that is the central equation of fluid mechanics, which is known as the Euler equation. So Euler equation is nothing but Newton's second law applied to fluids. Second law applied to fluids. So we know that according to Newton's second law, we know that the rate of change of momentum per unit volume should be equal to the force acting on per unit volume of the fluid. So what is the expression of rate of momentum of a fluid per unit volume? So if we multiplied rho by this rate of by this acceleration there dv dt, that gives you the rate of change of momentum per unit volume. And note that here you have to use Lagrangian derivative rather than Eulerian derivative, which appears here, and that has to be equal to the forces acting on it. So what are the forces? You may have some force like gravitational force, so which is also can be written in an expression like rho f. So f is the force per unit mass, so multiplied it by multiplying f by rho, you get force per unit volume. And there's another very important force is that comes from the pressure. You know that inside a fluid, if there is a pressure variation, that gives rise to motion. The fluid tries to move from regions of high pressure to regions of low pressure. So certainly this pressure induced by certainly this sort of motion is induced by pressure gradient, and the fluid tends to move in the direction of negative pressure gradient from high pressure to low pressure. So you expect there will be a which is expected to be proportional to minus grad p. And if you do a systematic derivation step by step, then you find that it's not only that it's going to be proportional to minus grad p, but it's minus grad p is the force per unit volume. So it has to be like this. So this is the famous Euler equation in fluid mechanics, and in MHD what we have to do is that we have to, because of the presence of magnetic field, we would have Lorentz force, so we have to add this Lorentz force term to this equation. So let us try to figure out what would be this Lorentz force per unit volume. So this Lorentz force that is given by an important formula of electromagnetic theory, J cross B. I'm sure all of you know that. And then for J, I think when you neglect this term, we have curl B is equal to mu 0 J. So J is given by curl B by mu 0. So if we use that, then we have this curl B by mu 0, and then we have to multiply it by curl B. And this curl B cross B, by using a vector identity, you can write it in a modified form. So this vector identity you will find discussed in any textbook of vector analysis. So I shall not get into a discussion of that. So if you use this vector identity, then you will find that this thing is going to be equal to this B square So from by looking at your vector analysis books, you can very easily show that this should be equal to this. So I'm leaving it for you to figure out. So now we have to combine this thing with this, put this extra term in our Euler equation for fluid mechanics. So now then what do we get? Let me write it down. So there is this rho, and then Lagrangian derivative of time. We very often use the Eulerian derivative. So by using this relation, we can write this as dv dt and then here we have this rho f, and then we have this minus grad p, and minus grad p and minus grad of this quantity. We can put them together, so we write them as yes. Well, that comes from, I think basically for this you have to use this formula of gradient of A dot B. It's given in all vector analysis books, and then you have to take A and B equal, then this term will give you B square, and if you work out this formula, you will see that this factor 2 comes there. Okay, and then the last term is going to be so compared to this Euler equation in fluid mechanics, you have these two extra terms. And what is the physical implication of this extra terms? So this extra term, this term appears with the pressure. So this implies that magnetic field also exerts a pressure. So this term is known as magnetic pressure. And what is this term? So to understand the significance of this term, let us consider that there is some uniform magnetic field in a region. And here B dot grad means that we have to consider a gradient as we move along the direction of the magnetic field. And if the magnetic field is uniform, that means that if you move along the direction of the magnetic field, then nothing is changing, so it will be 0. So this term is going to be 0 in the case of a uniform magnetic field. And instead of a uniform magnetic field, if you have a magnetic field which is bent like this, in some regions it's bent like this, then you can show that in that situation this term will be non-zero, and this term will have such a direction that it will again try to pull down this bend like this. So it will try to make the magnetic field line straight again, and that is the nature of tension. So you know that if you have stretched rubber band, it has a tension, and if you distort the rubber band a little bit with your finger, then as soon as you remove your finger, it will again try to become straight. So this is the term which tries to keep magnetic field line straight. It is like a tension. So this term is known as this magnetic tension. So in the first class, I already discussed some situations in which magnetic pressure and magnetic tension play an important role. So do some of you remember when in the first class when we discussed the importance of magnetic tension? Anyone remembers? Yes, yes.
So can you say that mu naught is an adiabatic invariant?
Yeah, that is also no. There is a different kind of thing called an adiabatic invariant, which is also used, which is also denoted by the symbol mu. But let us not get into a discussion of that. So mu 0 is just this magnetic constant, what is called constant of permeability or something like that. So anyway, so can someone remember where we encounter magnetic tension in the last lecture?
The nonlinear theory of magnetoconvection.
Yeah, that's right. So it's a magnetic tension. Because of magnetic tension, magnetic field lines try to remain straight, and that's why they oppose convection, and that property is very important to understand why there is not much heat transport in transports and why it appears dark. And we also encountered magnetic pressure. So someone remembers where we encounter magnetic pressure? Yes.
You showed that magnetic lines flow in a tube at the bottom of
Yeah.
convection layer, and then they go up.
Yeah.
So
Yeah.
at
Yeah, so that's right, that's right. So magnetic, so this magnetic pressure makes sure that inside the flux tube the gas pressure is less, and that gives rise to magnetic buoyancy. So we have already seen some applications of this. So anyway, so we have discussed some of this basic equation. So time derivative equation, P we shall not bother, so rho and V. Now we come to the most important equation of MHD, which is the time derivative equation of B. So what is that equation? Let us discuss that. So that time derivative equation of B, that goes by the name induction equation, and let us now write that equation. So apart from Maxwell's equations, another very important equation is Ohm's law. And about Ohm's law, many of you probably would have learned about Ohm's law in a continuum situation also. So usually when there is no magnetic field, it's like this. Without B, you know that the force on a charged particle is going to be like this, and if in a region there are many charged particles, so this force will act on all of them, and they will make all of them move and give rise to a current, and then one can show that in a continuum system the current density would be proportional to electric field E, and this being the conductivity, the constant of proportionality. And now if there is a magnetic field with B, then this F gets modified to Q E plus V cross B. So you expect that this Ohm's law also will be get modified in a similar manner. So in MHD, this is the version of Ohm's law which we use. And then again from this equation for current density we can write curl B minus curl B divided by mu 0. Then if we substitute that for J, then for E we could get this relation E is equal to curl B mu 0, this is J, and sigma we are bringing on this side and sigma here, and then there is this term. So this is the expression for electric field, and as I already mentioned that in MHD usually this electric field in the rest frame of plasma is very, very small. So it's not only small, we can even express this electric field in terms of other variables like B and V. So it's not an independent variable. So that's why we don't treat E as an independent variable in MHD. And now that we have got this expression for energy, we have to make use of another very important Maxwell's equation. So del B del T, and you know that this is equal to minus curl E. So this is the mathematical expression of this famous Faraday's law of electromagnetic induction. So that's why this equation which follows from this Faraday's law of electromagnetic induction, this what we are going to derive now is known as induction equation. So now for E we just substitute this expression, and then what do we get? So from this second term we would get this minus sign and minus sign, they cancel each other. So curl V cross B, and from this other term we would get this minus, so mu 0 sigma and curl B. So here we are making one simplification, that we are assuming this sigma to be a constant in space. If it is not constant in space, then when we are taking the curl, sigma will appear here inside rather than here. So that is that creates some additional complications which we have to consider in some situation, but let us not bother about that. So this is the induction equation, and by using the fact that divergence B is always 0, it can be shown that this can be written in the form minus del square B. So using a simple vector identity which we will find in any vector analysis textbook. So this is our induction equation, and since I have no space here, let me write down this other basic equation, or maybe I write it at the top, because this is the most important equation for us. Induction equation del B is equal to so now we have all this equation. So you have this variation of density, and that can one can derive another equation for variation of pressure, which we are not going to discuss in this lecture, and then time derivative equation of velocity field, and at last time derivative equation of a magnetic field. So if one initial state of the plasma is given, then you can figure out after some time what would be the state. So it seems like this is a completely deterministic problem. If we have an initial state, then by solving this deterministic equation, we can find the final state. But one puzzling thing we can mention that in fluid mechanics and MHD, we often encounter a situation, turbulence, that's where things, various things seem to be rather randomly. So it seems mysterious that the system is governed by a set of deterministic equations. So how do we have something like turbulence where it seems that things are becoming indeterministic? So that is a very big question in this field, and still quite a lot of research is being on turbulence in fluid mechanics and MHD. We still do not have a full theory of turbulence. So I thought that I shall just mention that. And now I think we have these two terms in the induction equation, and we would like to figure out which term is how important relatively these terms are, which term is larger and which term is smaller. So let us look at that question a little bit. So suppose we have some fluid in which this typical velocity field is given by V and typical magnetic field is given by B, and let us call L the length scale. Length scale means the length over which this velocity field, magnetic field, etc. vary substantially. So now we can try to make a rough order of magnitude of these terms. So let me write it down again. So what will be the order of magnitude of this term? So certainly we have a product of V and B, and then we are taking its spatial derivative. Taking spatial derivative means that we are dividing by the length scale. So this is going to be of the order of VB by L, and this is a double spatial derivative. So this is going to be of the order of B mu 0 sigma L square. So it's the double derivative. We take L squared here, and if we take a ratio of this, then we get a dimensionless number which is known as magnetic Reynolds number, which I introduced in the last lecture. Now you see how it comes. So those of you who have studied fluid mechanics must have encountered across this important dimensionless number, Reynolds number. So this magnetic Reynolds number is the analogous number in MHD, and it is usually indicated by this symbol curly Rm. So we have to take a ratio of this term. So we have VB by L, and we have to divide that by B by mu 0 sigma L square. So B cancels out and 1 power of L cancels out here. So what you are, I should put up probably approximation sign, then what you are left is that mu 0 sigma, and then this L comes, L V. This is what we are going to get, and this is electrical conductivity. Often one introduces electrical resistivity. for which often one uses a symbol rho, which is the inverse of 1 over sigma. So be careful not to confuse this rho with this density rho. So if you use this electrical resistivity, then you will have mu 0 LV and rho. So this is the expression of magnetic Reynolds number I pointed out. So when I also discussed this Alfvé's theorem, which holds if magnetic Reynolds number is very large, so it is a sorry, not sigma. Yeah, this is sigma. Oh, sorry, this is rho. So when resistivity is very small, then magnetic Reynolds number turns out to be large, but it also depends on the size of the system. So if the size of the system is very large, then also it turns out to be large. So if you make some order of magnitude estimate, then you find that this magnetic Reynolds number is much smaller than 1 for lab systems, and much larger than 1 for astrosystems. So what does that mean if this is much less than 1? That means that this is the negligible term. So in the lab situation, we can often write it like this, that in lab situation, this is the dominant term. So for instead of sigma, we can put rho here. So we would get this is the dominant, and it's approximately 0, and rho del square V. And in the astrophysical situation, you find that this is the dominant term. So we can write it in this fashion. That is why we find that magnetic field often behaves very differently in laboratory plasmas, in astrophysical plasma. So this is an equation, this is something which is very easy to interpret. I think this is the approximation sign, but if you use the equality sign, then we would get one of the very famous equations of mathematical physics, the diffusion equation. I don't know whether you have studied diffusion equation much in some course. So the diffusion equation implies that the magnetic field would diffuse away. So why is that? So you note that here is resistivity appearing there. So in any material in which there is plasma, there is some electrical resistivity, and in order to maintain the magnetic field, currents have to flow through this plasma. So unless you have some mechanism to maintain the currents will decay away due to this resistivity, and then the magnetic field also will decay away or diffuse away. So that is what is the significance of this equation. So which is very easy to understand, that in laboratory situation, this magnetic field just decays away unless you have some system to maintain the currents there. And what happens in astrophysical situation? So instead of approximation sign, if we use this exact sign, del B del T is equal to curl V cross B, then from this equation we can derive this famous theorem which we discussed in the morning, Alfvé's theorem. So it is not something too difficult to derive. If I had a time of something like half an hour or 45 minutes, then I could derive this equation on the blackboard in a completely step-by-step manner, but certainly, but since I don't have that time, I won't be able to derive that. So if you are interested in looking up this derivation, then I may mention that it's discussed in many books, and I have recently written an MSc level electromagnetic theory textbook, which is published by Springer. It's called Advanced EM Electromagnetic Theory, and I have a soft copy of that. Maybe I shall send a soft copy to Karthik and so that he can share it with you people. And this last chapter of this book is devoted to plasma physics and MHD, and all the things which I am discussing in this lecture, they are all discussed in this last chapter of this Advanced Electromagnetic Theory book. And although I discussed this Alfvén's theorem in the morning, let me again, since it's such an important thing, let me again quickly point out one more time so what is said. So suppose inside the plasma, which is treated as a continuum, we consider a surface with some magnetic field lines associated with it. So at times say Ti, and because of the motion, the materials which made up the surface, they would move, and after some time they would make up another surface at Tf, and there would be some magnetic field going through it. So Alfvén's theorem says that magnetic field which was at time Ti through this surface Bi dSi, that should be equal to the magnetic field through this surface at some later time Tf Bf. So it follows from if magnetic field obeys this equation. So was there any question? Okay, so that I have already discussed in the last class, and you remember the consequence of, very important consequence of that was that colloidal field gets stretched into toroidal field. So with that we are able to explain many aspects of sunspots. So to summarize, I think there are some three very important new concepts in MHD which are in addition to fluid mechanics, which you should remember. So let me again list these three concepts. So new concepts in astrophysical MHD. So astrophysical MHD means where this magnetic Reynolds number is very high. So in such situation, one is this flux freezing. As if magnetic field is frozen in the plasma, and when the plasma moves, magnetic field moves with it. And another is magnetic tension. And another is magnetic pressure. So you remember that these are the three very important new concepts, and we already saw that many phenomena of solar activity can be explained with the help of these concepts. And now I am almost at the end of my time, so let me just quickly mention some other astrophysical applications of MHD, so that you have some idea that MHD is important not only in solar physics, but in many other areas of astrophysics. So Professor Srinivasan must have discussed this problem of stellar collapse. So under certain circumstances, a normal star, when its nuclear fuel is exhausted, it may collapse to become a white dwarf or a neutron star. So when that happens, what will happen to the magnetic field of the star? So let us consider, suppose we have a somewhat of a large star, a normal star, which collapses and becomes a much smaller star, white dwarf or neutron star. So if Alfvén's theorem holds, then what happens is that whatever was the magnetic flux passing through this star, so after it becomes much smaller, the same magnetic flux will have to pass through it. And what is the magnetic flux? It's approximately this area of in the middle is pi r square. So it's essentially this pi r squared b that will have to be conserved when the star collapses. So here we have here we have the initial radius r I squared and initial magnetic field b I. That should be equal to this final radius squared and b final. So now in the case of a normal star, you know that typical radius of the sun is of the order of 10 to the power 6 kilometers. It's a little bit less than that, and we pointed out that the magnetic field is of the order of something like 10 to the power minus 3 Tesla. And if you get a neutron star, so the neutron star radius is of the order of 10 kilometers, and we want to figure out what this magnetic field is like. So here Ri is this, so you put 10 to the power 6 squared, and Bi is this 10 to the power minus 3, and this is equal to 10 squared, so you just put 10 squared and this Bf, and it's easy to see that in this situation you will get Bf to be of the order of 10 to the power 7 Tesla. So when a star, this normal star collapses, you expect the collapsed star to have a huge magnetic field, provided this magnetic flux is frozen and Alfvén's theorem holds. So Professor Srinivasan must have talked about pulsars. So because of the high magnetic field of neutron stars, they often act as pulsars. And for most of the normal pulsars, the magnetic field is estimated to be somewhat less than that, maybe more of the order of 10 to the power 4 Tesla. That's because when the ordinary star contracts to become a neutron star, it's often a catastrophic event. So many things may happen. So you don't expect the magnetic field to be conserved completely. So the final magnetic field turns out to be a little bit somewhat less than that, but still we use this concept of flux freezing to understand why this sort of compact stars like white dwarfs and neutron stars have a very large magnetic field. And then I shall stop by just considering one more application of MHD to interstellar medium. So you all know that these gas clouds in the interstellar medium collapse to form stars. I don't know whether in some lectures this topic is covered. Was there discussion of star formation in any lecture? Okay, so whose lecture, which one? Okay, so he discussed star formation also. So basically then we have a situation of a collapse of interstellar cloud. So collapse of interstellar cloud, it collapses eventually to give rise to stars. And you know that because of the rotation in galaxies, in spiral galaxies, usually the interstellar clouds also have some angular momentum associated with it. So an interstellar cloud would be rotating, and you all know the standard result that if an rotating object shrinks in size, then because of the conservation of angular momentum, it starts rotating faster and faster. So if the angular momentum is conserved, then we expect that as it shrinks, its angular velocity will go as 1 over r square, because angular momentum is given by omega r square, and we are expecting that to be constant. And then as the rotation speed increases further and further, we expect the centrifugal force also to go up. So how would centrifugal force go up? So centrifugal force is given by omega square r, and omega increases as 1 over r squared, so it increases at 1 over r squared and r, so it increases at 1 over r cube. So as the gas cloud collapses, the centrifugal force becomes larger and larger, and the gravitational force also becomes larger, and from Newton's law we know that gravitational force also will increase. So gravitational force, from Newton's law of motion, we know that it will go as 1 over r square. So as the gas cloud is collapsing, both the centrifugal force will keep on increasing and gravitational force will also keep on increasing. But since this goes as at a higher power, inverse power of r, you know that centrifugal force will keep on increasing at a faster rate than the gravitational force. So eventually, after this gas cloud has collapsed sufficiently, the centrifugal force would become larger than the gravitational force. So the gravitational force will not make the cloud collapse anymore. This centrifugal force would hold the collapse. So if the centrifugal force becomes so large and holds the collapse, then how do we get stars? How can the gravitational collapse of the star continue? So we believe that it continues because of the fact that this interstellar gas cloud would also have some magnetic field associated with it, and as it is rotating, the magnetic field would get tangled and have this kind of a structure, and to get increasingly more and more tangled. So because of the tension of this magnetic field line, it will try to stop, try to break this increasing rotation, and by detailed mathematical calculations one can show that actually this magnetic field tries to break this increasing rotation of this collapsing cloud, and that's why the centrifugal force cannot increase so rapidly, and that's why this gravitational collapse can continue and eventually form stars. So if there are no magnetic fields in the astronomical universe, then stars could not form, and then certainly we would not be here today to discuss MHD. So in some sense, we are all children of astronomical magnetic fields. Without astronomical magnetic fields, we would not even exist here today. And so that gives you some idea of the importance of astronomical magnetic fields and the subject of MHD, with which we study this astronomical magnetic fields. So with that, I shall stop, and if you have any questions, I shall try to answer. Okay, that I already discussed, that in a plasma, we, instead of using E and B as parameter, so we use only B, because in the rest frame of the plasma, electric field is going to be very small, and we can also, the small electric field we can express in terms of this other variables, which is not an independent variable. Yes.
What are the conditions under which flux freezing may not hold?
So flux freezing is, as I said, that is the flux freezing his whole condition is that magnetic Reynolds number has to be much larger than 1. So certainly in laboratory plasmas that is not the case. So in laboratory plasmas it would not hold, and apart from electrical resistivity also there is, one can show that in a plasma if there is quite a lot of turbulence, and the turbulence also to some extent plays a role similar to the electrical resistivity. So if the plasma is very turbulent, then that also may lead to a breakdown of this Alfvén's theorem of flux physics. That's why we believe that when a normal star collapses to a neutron star, it's a violent process which may involve turbulence and other effects, and that's why we expect this flux freezing to be approximately whole, but not whole very strictly. Yes?
When we have to discuss convection, so due to temperature gradient.
Yes.
So will a temperature get coupled to these equations, or that has its separate independent?
Oh, well, I think I think if you systematically learn stellar structure theory, if you look at the standard textbooks on stellar structure theory, so one in my book Astrophysics for Physicists also there is a discussion, and some of the classic textbook on stellar structure theory is by Martin Schwarzschild. So in that book this is discussed that if you have a gas, and if you across the gas, if you create a temperature gradient, if the bottom is hotter than the top, then how much hotter it will have to be to start convection. And many of you might have heard the name of Karl Schwarzschild, who found this famous solution of Einstein equation in general relativity, when Einstein himself thought that the equations are so complicated that it may not be possible to find solution. It's this same gentleman, Karl Schwarzschild, who looked at this problem, so how strong the temperature gradient has to be to start convection, and he derived that condition, and that is known as the Schwarzschild condition. So this Schwarzschild conditions determines whether there would be a convection in a region of the star. So when people were building models of stars like the sun, they found out that from something like 0.7 solar radius to the surface, according to Schwarzschild condition, this will be a region unstable to convection, and heat would be transported by convection.
Professor,
Yes.
when we look into the imagery of like active galactic nuclei, where the plasmas can be relativistic, in that condition, that approximation can't be.
Yeah, that's right. There you have to consider more complicated thing, and in fact, not only special relativistic consideration, you also have to include general relativistic consideration. So this in the last few years, this general relativistic MHD, there have been quite a lot of research, and you might have learned about that some active galaxies, there are some huge jets coming out from the central regions of the galaxy. So if you want to study how these jets are produced, then one has to consider this general relativistic MHD. And in the last few years, there have been quite a lot of work in this very complicated subject, how these jets are produced. So any other questions? Okay, so then let us break. So, yes.
When you were specifying the fluid state,
Yes.
you did not take time into account, that rho of x comma only x, that is the function.
Okay, yeah, because I was considering the state at a particular instant of time, so certainly these things will change with time. So when you consider variation of space and time, then certainly they are functions of time. But at a particular time when you specify the state will be a function of position. So okay, so enjoy the rest. Yes.
You told the actual magnetic field for the neutron star comes out lesser. But
Yes, that's right.
why was that?
because it's a violent process. So when the normal star collapses to become a neutron star, so you don't expect there may be turbulence, and in such a situation you don't expect Alfvén's theorem to be hold exactly, but it will hold only approximately. That's why this magnetic field turns out to be lower than what we expect from Alfvén's theorem. So Professor Srinivasan has discussed about pulsars. So because of the existence of magnetic fields, the neutron stars behave as pulsars. So most of the pulsars, the typical magnetic field is estimated to be about 10 to the power 4 Tesla. So there are some pulsars, some millisecond pulsars, which have much higher magnetic field. So did he discuss also millisecond pulsars? So he himself did very pioneering work on that. Okay, so enjoy the rest of the summer school.